In this video, I am taking problem 1 of Bode plots. So this is one example problem. Sketch Bode plot for the following transfer function and determine the system gain k for the gain crossover frequency to be 5 radians per second. So given transfer function is g of s is equals to k s square by 1 plus 0.2s into 1 plus 0.02s. So here for this transfer function we have to draw Bode plots and also we have to determine the system gain k. So for the gain crossover frequency to be 5 radians per second. So step 1 is, so here we have to follow the steps to draw the Bode plots. So step 1 to draw the magnitude plot, step 1 is, so given open loop transfer function is, so here, so whatever the open loop transfer function is given, we are writing the same. So g of s is equals to k s square by 1 plus 0.2s into 1 plus 0.02s. So here this we have to write in terms of time constant form. So time constant form, if we express the same in time constant form, so k s square by 1 plus s t1 into 1 plus s t2. So here if we compare these two equations, given transfer function and the standard form of the time constant form, so instead for t1 we have 0.2 seconds and for t2 we have 0.02 seconds. So t1 is one time constant and t2 is one time constant. T1 is 0.2 seconds and t2 is 0.02 seconds. So open loop transfer function in frequency domain is, so to draw the Bode plots, so we have to change the transfer function. So we have to convert that to frequency domain analysis. So for that replace s with j omega. So here given, so transfer function is a s domain function. So for s we are replacing that with j omega. So g of j omega is equals to k. So for s we have to keep j omega square by 1 plus 0.2 for s, j omega 1 plus 0.2 0.02 for s, again j omega. So this is frequency domain. So transfer function in frequency domain or otherwise omega domain. So g of j omega equal to k j omega square by 1 plus 0.2 j omega into 1 plus 0.02 j omega. So first we keep k equal to 1. So k is equals to 1. So whatever the k is there, first we solve for k equal to 1. So if we put k equal to 1, g of j omega becomes j omega square by 1 plus 0.2 j omega into 1 plus 0.02 j omega. So this is step 1 in the Bode plots. Next step 2. Coming to the step 2, so we have to formulate the tabular column. So first column is serial number, so second column is term, third column is corner frequency in radians per second, and fourth column is slope in radians per second, and change in slope in dB per decade. So here slope dB per decade and change in slope is so dB per decade. So here the different terms are, so what are the different terms? So here we are writing these terms from the transfer function. So if you see this, so j omega square is one term, 1 by 1 plus 0.2 j omega is one term, 1 by 1 plus 0.02 j omega is another term. So altogether we have three terms here. So first term is j omega square, second term is 1 by 1 plus j 0.2 omega, and third term is 1 by 1 plus j 0.02 omega. So here corner frequencies. So next column is corner frequency, which is in radians per second. So for this term there is no corner frequency, so keep dash, small hyphen. So for this corner frequency, so this is first corner frequency omega c1, let it be omega c1, which is equal to, so time constant, time is t1 is 0.2 and 1 by t1 is w corner frequency. So omega c1 equal to 1 by 0.2, 1 by 0.2 which is equal to 5 radians per second is first corner frequency. And similarly second corner frequency is omega c2, omega c2 equal to 1 by 0.02, 1 by 0.02, so which is equal to 50 radians per second is higher corner frequency. So this is the lower corner frequency and this is the higher corner frequency. So first corner frequency and second corner frequency. So here coming to the next column, which is slope, which is in radians per decade. So here it is a numerator term and there is a power 2. So numerator term, that's why it is 20 dB per decade, and power 2 is 2 into 2. So 20 into 2 is 40 dB per decade is the slope for this term j omega square. And the next term is 1 by 1 plus j 0.2 omega, which is a denominator term. So denominator term, so slope is minus 20 dB per decade. And for next term is 1 by 1 plus j 0.02 omega. This is also denominator, first order denominator term. So that's why minus 20 dB per decade. Now next column is change in slope, which is in dB per decade. So here this is the first term, so it continues, so there is no change in the slope, so is dash. So next, so this minus 20 is added to 40, so that becomes the change in slope here. So 40 minus 20, 40 minus 20 is 20, so change in slope. So after effect of this term to this term is 20 dB per decade. So once this term is added to this term, and now the slope of the magnitude becomes 20 dB per decade. So again, so after adding this term at omega equal to 50 radians per second, so effect of this term comes into the picture. So up to 5 radians per second, only this term is affecting the magnitude. So at 5 radians per second onwards, this term affects the magnitude and slope changes to 20 radians per second. And after 50 radians per second frequency, third term affects the magnitude. Now it is so 20 minus 20, 20 minus 20 is 0. So that is the change in the slope. So slope, so magnitude goes with 0 dB per decade from 50 radians per second onwards. So next, that is about step 2. So coming to the step 3. So here choose a low frequency omega L such that omega L is less than the first corner frequency omega C1. Now we have to choose one arbitrary frequency whose frequency is less than the WC1. So WC1 is 5 radians per second and WC2 is 50 radians per second. So we have to choose one arbitrary frequency whose value is less than 5 radians per second. So I'm taking that as sum. Let omega L equal to 0.5 radians per second. Let A is equals to, now we have to find the magnitude at omega L and omega C1. So let A equal to, so G of J omega, magnitude of G of J omega in decibels. So here we have to draw a magnitude plot for this transfer function and also phase plot for this function. So now we are focusing on the magnitude plot. So magnitude plot, so A is equal to, let A equal to magnitude of G of J omega in decibels. So in decibels means, so for the magnitude we have to take log and after that we have to multiply with 20 to get in decibels. So at omega equal to omega L. So now we have to get that magnitude at omega L before omega C1. So A equal to 20 log J omega square. So 20 log J omega square. So up to lower cutoff frequency, so WC1 only this term affects. So up to omega C1. So omega C1 is 5 radians per second. So up to 5 radians per second only this term is affecting the magnitude. So that's why we have to take only that part, that term. So 20 log J omega square. So A equal to 20 log, if you take only magnitude, so remove the J, so it becomes omega square. So 20 log, so omega is, so omega L is 0.5. So replace omega as 0.5. So 20 log 0.5 square. So this becomes 40 log 0.5. So which is equal to minus 12 decibels. Next, similarly we have to get the same at W equal to WC1. So WC1 is 5 radians per second. So WC1 is 5 radians per second. So here WC1 equal to 5 radians per second. So we have to take solve for magnitude at that frequency omega C1, which is equal to 5 radians per second. So again A equal to 20 log omega square. So A equal to 20 log omega is 5 radians per second, 5 square. So if you take this 2 power 2 before this log, it becomes A equal to 20 into 2 is 40 log 5. So which is equal to 28 decibels. So up to omega C1, which is 5 radians per second, only first term affects the magnitude. Next, now after omega c1, so second terms comes into the picture. It affects the magnitude. Now there is a change in the magnitude and also the slope. So at step 4 is at omega equal to omega c1. Again you get the same information here, value a equal to 20 log omega square, which is equal to 20 log 5 square. So again a equal to 25 decibels, a equal to 25 decibels. You get the same information here. Now at omega equal to omega c2, now we have to calculate the gain at omega c2. So this is the formula to find gain at omega c2. A equal to slope from omega c1 to omega c2 into log omega c2 by omega c1 plus magnitude at omega equal to omega c1. So this is the formula to find the magnitude at omega c2. A equal to slope from omega c1 to omega c2 into log omega c2 by omega c1 plus a, again magnitude at omega equal to omega c1. So a equal to slope from omega c1 to omega c2 is, so from the table we can get that. So this we have to take slope from omega c1 to omega c2. So change in the slope. So we have to take this slope 20. So 20 slope from omega c1 to omega c2 is 20 into log. So omega c2 is 50 and omega c1 is 5. So here we can get these values from the tabular column. So omega c2 is 50 and omega c1 is 5. So here 20 into log 50 by 5 plus, so a at omega c1. So a at omega c1 is 28. So add that to 28. Now a becomes 48 decibels. So magnitude at omega c2 is 48 decibels. Now this is about step 4. So next step 5. So we have to solve step 5. So step 5 is, so we completed all the terms. Now we have to take one more arbitrary frequency whose value is more than the WC2. So choose a high frequency omega h such that omega h is greater than omega c2. So let omega h is equal to, omega c2 is 50. So from the tabular column omega c2 is 50. Now we have to take one more frequency wh, omega h, which is greater than 50. So here I am taking that value as 100. So omega h is equals to 100 radians per second. So again now we have to calculate the magnitude at omega equal to omega h. So I am using the same formula where I use it to solve for the magnitude at omega c2. A equal to slope from omega c2 to omega h into log omega h by omega c2 plus a at omega equal to omega c2. So here a equal to, so this is the gain, so magnitude at omega equal to omega h. A equal to slope from omega c2 to omega h into log omega h by omega c2 plus gain at omega equal to omega c2. So a is equals to, so again if you see from the tabular column, so from the tabular column, so omega c2 to omega h, so change in the slope is 0. Change in the slope is 0. So that's why, so here slope from omega c2 to omega h, slope from omega c2 to omega h is 0 into log. So wh value is 100 and wc2 value is 50. So wc2, so here from the table wc2 value is 50. So here 0 into, so 0 into log of 100 by 50 plus, so at omega equal to omega c2, magnitude is 48. So at omega equal to omega c2, so magnitude is 48. At omega equal to omega c2, a equal to 48. So take that value as 48. So now it becomes 0. So 0 into something is 0 plus 48. So a equal to 48 decibels. Now we have to take get the values for the phase plot. So after getting the values for the phase plot, so we can draw Bode plots, that is magnitude plot and phase plot. So phase plot, so the phase angle of g of j omega as a function of omega is, so pi. So I am taking that phase angle as some pi equal to phase angle of g of j omega. So angle of g of j omega, if you see the transfer function in omega domain, so this is the transfer function in omega domain. So this phase angle is 180 degrees, minus tan inverse 0.2 omega by 1 minus tan inverse 0.02 omega by 1. That becomes the phase angle of g of j omega. So here phase angle of g of j omega is equals to, so is equals to 180. So here it is 180. So it is a numerator term and there is a power 2. So that's why 90 into 2 is 180 minus. So this denominator, if you take this denominator phase angle to numerator, it becomes minus tan inverse 0.2 omega by 1. So minus tan inverse 0.2 omega by 1 minus. Again one more term is there in the denominator. So phase angle of that is tan inverse 0.02 omega by 1. If you take that to the numerator, it becomes again minus tan inverse 0.02 omega. So finally phase angle of the given transfer function in omega domain is, so pi is equals to angle g of j omega equal to 180 minus tan inverse 0.2 omega minus tan inverse 0.02 omega. So here if you take the different values for omega, so first serial number is 1, 2, 3 up to 6, and now we have to take different values for frequency. So generally we take the same values, so whatever the values we have taken for the magnitude plot, we take the same values for same values of omega here also. So 0.2, 0.5, 1, 5, 10, 50, 100. So these are the different values of omega in radians per second. Now substitute, so first we are calculating tan inverse 0.2 omega. So keep omega equal to 0.5, we get 5.7, take omega equal to 1, we get 11.3, and if it is 5, 45. So for these values of omega, we are calculating tan inverse 0.2 omega. So similarly for these values of omega, we are solving for tan inverse 0.02 omega. So after getting these two values, just substitute these two values here. So 180 degrees minus, so tan inverse 0.2 omega minus tan inverse 0.02 omega. So to get when omega equal to 0.5, so what is the phase angle means? So 180 minus 5.7 minus 0.6. So we get 174 degrees. So similarly, when omega equal to 1 radians per second, phase angle is 180 degrees minus 11.3 minus 1.1, which is equal to 168 degrees. So for omega equal to 5 radians per second, phase angle equal to 180 degrees minus 45 minus 57 equal to 130. So similarly for different values of omega, so these are the phase angles. Now we have to take a semi-log graph. So semi-log graph. So this is the semi-log graph. Now we have to draw magnitude plot as well as phase angle plot. So magnitude, so I am taking the reference here. So this is the origin, and on x-axis, y-axis, so I am taking the magnitude. So 10 decibels, 20 decibels, 30, 40, 50, and negative axis minus 10 decibels and minus 20 decibels. So similarly for the phase angle curve, so I am taking this as the reference. So this as the reference, and on y-axis, so 0 degrees, 40 degrees, 80 degrees, 120 degrees, 160 degrees and 200 degrees. So 1 unit, so 1 unit equal to 40 degrees. So here 1 unit equal to 40 degrees. And x-axis scale is, so this is x-axis scale. I am taking this as 0.1. It is a non-linear scale. X-axis is non-linear scale and y-axis is a linear scale. And 10 times of 0.1 is 1, and 10 times of 1 is 10, and 10 times of 10 is 100. So here the different frequencies are, so omega L. So omega L is equals to first frequency, omega L equal to 0.5 radians per second, and omega C1 is 5 radians per second, and omega C1 is 5 radians per second, and omega C2 is 50 radians per second, and omega H is equals to 100 radians per second. So that's why, so I have to take, so 5 radians per second, 0.5 radians per second, and 5 radians per second, 50 radians per second, 50 radians per second, and 100 radians per second, 50 radians per second and 100 radians per second, 100 radians per second, that is omega H. So omega L is 0.5, the omega C1 is 5, omega C2 is 50, and omega H is equal to 100, that is abscissa scale. Now So omega L, at omega L 0.5 radians per second, so we have to check the magnitude. So magnitude at omega equal to omega L, which is 0.5 radians per second. It is minus 12 decibels. So we have to draw that, we have to locate that point. So at omega L equal to 0.5. So at omega L is equals to 0.5. So here it is minus 12. So it is minus 10, minus 20. So here it is a minus 12 point, minus 12 decibels. So similarly at omega C1 equal to 5 radians per second, omega C1 equal to 5 radians per second, magnitude is 28 decibels. So if you see the magnitude, so magnitude equal to 28 decibels. At omega C equal to omega C2, so omega C2 equal to 50 radians per second. So at omega C2 equal to 50 radians per second, magnitude is 48 decibels. So magnitude, if you see the magnitude, so magnitude is 48 decibels. So this is 50, so 48 decibels. So that is the highest value. So that's why I am taking scale from minus 20 to 50. So minus 20 decibels to 50 decibels. So lowest value is minus 12 dB and highest value is 48 dB. So that's why I am taking alternate scale from minus 20 decibels to 50 decibels. So here after taking that, so omega h, so omega h is 100 radians per second. So omega h is equal to 100 radians per second. So at 100 radians per second, value is again 48 decibels. So 100 radians per second, value is again 48 decibels. Now we have to join these points. So this point and this point with straight lines, and this point like this. Now this becomes, after joining you get a curve, magnitude plot like this. So this one and this one. What is the slope of this is, so here I am taking k value as 1. So slope of this curve is 40 decibels per decade. So at this point, at omega C1 equal to 5 radians per second, so second term comes into the picture, effect of second term comes into the picture. Now there is a change in the magnitude. So slope changes to 20 dB per decade. So minus 20 dB per decade is added to 40 dB per decade. Now slope is 20 dB per decade. With that slope, magnitude travels. At omega C equal to omega C2, which is 50, at omega equal to omega C2, frequency is 50 radians per second. So at that time, third term comes into the picture, and again the slope changes. So minus 20 is added to 20, now it becomes 0. So magnitude is traveling with 0 dB per decade. So again phase angle plot. So phase angle plot, if you see the phase angle plot, at omega equal to 0.5, at omega equal to 0.5, angle is 174. So angle is 174. So here if you see the angles 0, 40, 80, 120, 160, 200. So here at 0.5 radians per second, phase angle is 174. So that's why at 0.5 radians per second, angle is 174. So phase angle is 174. So phase angle is 174. At omega equal to 1 radians per second, phase angle is 168. At omega equal to 1 radians per second, this is 1 radians per second. So phase angle is 168. At omega equal to 5 radians per second, so WC1, at 5 radians per second, so phase angle is, so at 5 radians per second, phase angle is 130. So here phase angle is 130. At omega equal to 10 radians per second, at omega equal to 10 radians per second, phase angle is 106. Phase angle is 106. So here 10 radians per second, phase angle is 106. At omega equal to 50 radians per second, phase angle is 50. Phase angle is 50. At omega equal to omega h, which is equal to 100 radians per second, phase angle is 30. So that's why I am taking the range of angles in degrees is from 0 to 200 degrees. So minimum angle I am getting as 30 degrees and maximum 174 degrees. So that's why I am taking scale from 0 degrees to 200 degrees. So if you join that curves, so here you should not take straight lines, so we have to take a curved lines. So this becomes the phase plot. So upper one is a magnitude plot and lower one is a phase angle plot. So both combinedly called as a Bode plot. So magnitude plots should be in decibels. So here magnitude is in decibels. So in problem he is giving one more question. So that question is, so determine the system gain K for the gain crossover frequency to be 5 radians per second. So 5 radians per second. We have to find that. So first of all we should know what is a gain crossover frequency. So gain crossover frequency, which is indicated with omega GC, the frequency at which the magnitude of the open loop transfer function is unity. So the frequency at which the magnitude of the open loop transfer function is unity. If magnitude is unity, the corresponding frequency is called as a gain crossover frequency. But here we have the magnitude in decibels. So that's why there is other definition. It is the frequency at which the dB magnitude is 0. In terms of decibels, if the magnitude is 0, then the corresponding frequency is called as a gain crossover frequency. Now, so by seeing this curve, we can say what is the gain crossover frequency. So at this point the magnitude is 0, so the corresponding frequency is 1 here. So the corresponding frequency is 1. So at 1 radians per second the magnitude in decibels is 0. So if we take K as 1, we are taking gain crossover frequency is 1 radians per second, because at 1 radians per second the dB magnitude is 0, but he wants the gain crossover frequency to be 5 radians per second. So means at 5 radians per second the magnitude should be 0. At omega C1 at 5 radians per second the magnitude should be 0. So that is what he wants. So means we have to get this magnitude plot down by 28 radians, 28 dB. So here at omega C at 5 radians per second the magnitude is 28 dB. So we have to get that down that to 0. Means, so here we have a formula for that. So 20 log K is equals to minus 28 dB, because we have to get the magnitude plot down by 28 decibels. So that's why the system gain K for the gain crossover frequency to be 5 radians per second. So if the gain crossover frequency to be 5 radians per second, so what is the value of K? Means 20 log K equal to minus 28 dB. Log K equal to minus 28 by 20. So K equal to 10 power minus 28 by 20. So here K equal to 0.0398. If K equal to 0.0398, so gain crossover frequency is 5 radians per second. If K equal to 1, gain crossover frequency is 1 radians per second. So here if for omega equal to 1 radians per second, gain crossover frequency, that becomes the gain crossover frequency, because gain is 0 in decibels. So at omega C equal to 5 radians per second, if gain crossover frequency is 5 radians per second, and now so means magnitude is 0 decibels. So K for that magnitude plot, K equal to, we have to take the K value as 0.0398.